physics that is completely diametrically opposed to the superstring concept.
And allow me a bit of a thought experiment here. We thought, my intuition says that when you propose a theory of everything, the kind of prediction you want to make involves a kind of leap of conceptual understanding that Einstein did. So for example, you want to come up with something like space-time and that gravity bends space-time. So it's not merely that you have this beautiful mathematical framework, but that framework allows you to rethink how you see reality enough to make a prediction that's about the macro world.
I mean, just come up with something like space-time. You know, there's one idea, for instance, to say the space and time are real. They emerge from entropy. Yeah, that's a new way of thinking, and maybe there's some validity in how people think about it. But in the end, it's just an idea, and that's the real key thing. And as you say, it has to tie to a macro world. You have to validate. If you don't validate, it's a crazy idea. Theorists are incredibly creative, smart, wonderfully interesting people, but I don't care. I want a measurement that validates the idea, because there are so many. If you read the journals, there are so many theoretical papers, all these nifty ideas that somebody, one that was recently I liked, and it might still be true, was that dark matter, that, our simple model of dark matter is that there's a subatomic particle out there that's heavy and it's floating around and it's causing gravity. So well, maybe there's complex dark matter, which means there's a whole dark sector, so there are dark atoms and they interact with one another. And that is a nifty idea, and I love it. And that was all the rage for a while. And we looked at it, and it may still be true, but the simple ideas have been invalidated because we tested it and it doesn't work. Same thing, there was a talk about large extra dimensions. The reason that gravity is so much weaker than the other forces was, well, maybe gravity can sneak into more dimensions than the other forces.
It leaks into those dimensions.
That was a cool idea. I mean, but that's the point, is you have these lovely, cool, interesting ideas that constantly die. And so, I would love for a new nifty idea to be the idea, but I don't know how to pick it out of the hurricane of wrong ideas.
I mean, that's the real beauty of science. It really is. I mean, the theories kind of get some of the glory sometimes, but the real beauty emerges from the experiment and the demonstration that the theory is correct.
And there are two directions. You're talking a top-down. Someone comes up with this big idea that's testable, but you also have the other way that science advances, and it's not with a theory that is then tested. It's with the, that's weird. For instance, either in the 1930s with Fritz Zwicky or in the 1970s with Vera Rubin, she did a simple thing. She said, how fast are galaxies rotating? It's an easy thing to calculate. You can literally calculate that with high school physics. And you get an answer, and then you measure it, and it's wrong. And so that's the, wow, I don't know what that is. And that led to the hypothesis of dark matter. Now, dark matter is not a theory of everything, but it's a clue. It's a powerful clue. We should tug at that thread. Maybe our entire theoretical edifice unravels, or maybe it doesn't. Maybe it's just a snag, and we can fix what we have now. I'm not sure. So that's another option, is to simply look at many measurements that are very precise and find ones where the outcome and the prediction with established theory disagree, and that is a clue.
Before we leave the topic, we got to talk about string theory. In your view, is it basically dead? As I understand, one of the primary flaws of string theory, outside of the testable experiments that we're talking about, is because it relies on these unobserved extra dimensions. There was a hope that it uniquely could explain our universe, but it turns out this, quote, landscape, there's an enormous so-called landscape of possibilities it leads to. And so it renders the theory basically unproductive.
presentation recently. Love it. The observation of gravity waves, and it was from two neutron stars orbiting and coalescing. And so they made gravitational waves, fantastic. But they also, because they were not black holes, they were neutron stars, they hit and exploded, gave off a tremendous bright flash of light. And so astronomers saw the flash. Gravitational wave astronomers saw the ripples of space-time. It was 140 million light years away, which means light would have traveled 140 million years to get here. And two incidents, light and gravity, arrived within 1.7 seconds of one another. And that tells you that gravity travels at the speed of light. That was a brilliant, fantastic measurement. Now, we thought gravity traveled at the speed of light, but now we have a measurement, we proved it, and damn it, I am impressed.
Our universe is so fascinating. Speaking of which, let's move on. Antimatter. Let's talk about it. You've talked about it several of your lectures from different angles, including the dark energy crisis, including empty space and vacuum and so on. Let's look at the empty space angle. So, it turns out that empty space is not empty.
It's true, which is kind of bizarre.
Can you speak about what do we know about what makes up empty space?
That's a hard question because we don't know what space is. Start out. Let's just start out with something. Assume that space is not quantized, okay? Now, it probably is, I don't know, but we've got to start with somewhere. So let's start out with sort of the space of calculus, the space that you can divide forever. The modern version of quantum mechanics is called quantum field theory. And it postulates that A, space exists. Then it postulates that within space there exist fields for every known subatomic particle. So there is a photon field, there's an electron field, there's an up quark field, there's a down quark field, there's all the fields. And those fields can vibrate. And when they vibrate, those are the subatomic particles. So an electron field vibrating in a characteristic way is an electron. Now, it's also possible for the electron field to vibrate not in a characteristic way, but in a way that's still vibrating, but it's not an exact electron. So this is what we call virtual particles. Now, virtual particles, there are lots of ways to talk about them. The way I'm talking about now is the most correct and the most sophisticated way that we can talk about them. I will talk about them briefly in a simpler way to help. But right now, that's the important thing, is that there are these fields. Specific vibrations are the known particles. Vibrations that are a little different are these virtual particles. They're particles that don't truly exist. And so that is what we think space is. There's all of these fields. They're all vibrating a little. If you insert the right amount of energy, you can get it to vibrate in the characteristic way and make that subatomic particle. But even when you don't, there something like 0.29, and that means there's a good chance it's between 0.5 and 1, which means it's consistent with 1. So they are improving their measurements.
Well, if I can, I would love to take a bit of a tangent on that topic because I went down a rabbit hole watching some of your videos on antimatter, and I mean, Fermilab was the hub for the production of antimatter for quite a while. I saw that NASA said that the global estimate for the current rate of production of antimatter is 1 nanogram per year. Can you speak to how hard was it to make antimatter? And also, you did mention in the video that if matter and antimatter meet and produce a lot of energy, I think 20 grams of antimatter is equivalent to 1 megaton nuclear warhead in terms of explosive energy. Yeah, so all of those questions together. So how hard is it to produce antimatter?
It's freaking hard. Okay. All right. So here's the deal. So at the time, until 2011, Fermilab was the most powerful anti-proton production facility on the planet. Every 2.3 seconds, we would smash 10 to the 13 protons into a target, and we would get out 10 to the 8 antiprotons. So basically, in order to get a single antiproton, we needed to smash 100,000 protons into the material. So every 2.3 seconds, we would get of order 10 to the 8 antiprotons. And what we would do is we would collect them over the course of 12 hours or so. And we would get, in the end, and we would have to collect them and cool them down and so forth, of order 10 to the 12 antiprotons every 12 to 24 hours. So 10 to the 12 sounds like a lot. It really does. That is a trillion. But you need to remember that a gram of antimatter is 10 to the 23 antiprotons. So that means over the course of a day, we were able to create something like 100 billionth of a gram. And so if we did that for a year, then that would be about a nanogram. So about a nanogram a year, give or take.
My countermeasures are ready,
That's a reasonable
even if you
estimate.
are not.
So a nanogram, 1 billionth of a gram. So that means at that rate, with that facility, it would take a billion years running with very little downtime to make a single gram of antimatter. If you combine 1 gram of antimatter and 1 gram of matter together, the energy release is equivalent to the combined Hiroshima and Nagasaki explosions. So that tells you, if you wanted a megaton, you need about 25 times more. So you would have to run for 25 billion years to get a megaton of explosive power.
Let me lay it all out because I think it's pretty interesting actually. This is a NASA estimate of how much it costs to produce antimatter. So looking at all the cost of the accelerator, everything combined together, to do enough for a 1 megaton antimatter bomb is such a thing it will be impossible on the order of 25 grams, like you mentioned.
The dawn has arrived.
Based on a NASA estimate, $1.5 quadrillion. By the way, NASA wasn't talking about a bomb. It's just NASA was talking about the estimate, the cost of $62 to $63 trillion per gram of anti-hydrogen. Actually, is what they're referring to. So compared, I was looking at estimates. The current best estimate is how much it takes to produce a 1 megaton nuclear warhead. Everything combined is about $10 to $50 million in the United States. So you're talking about difference in terms of a weapon with equal power, $50 million versus $1.5 quadrillion. To me, what's interesting, weapons is just one indication of this. One other possibility, and NASA also writes about this, is the use of antimatter in propulsion systems.
Right.
Just like you can use nuclear fission and maybe even nuclear fusion down the line. In propulsion systems, I saw that 1 gram can help get us to Alpha Centauri star system. If we can get to 0.2 times the speed of light in 20 years, I mean, it would take us 20 years to get to Alpha Centauri. Is so we should mention that it's extremely compact. It has the obvious downside that it's extremely costly to produce. We don't know how to do that kind of scale.
Right.
The upside is it's compact.
Very powerful. So the short answer is it's not a physics problem, it's an engineering problem. So I have people. Okay, but no. The truth is that antimatter, if you are able to assemble it and store it, sure, it would be able to take that antimatter, heat up matter, and shoot it out the back of a rocket, and it would, do what rockets do, and it would make us go quick, and that would be fine.
And we should mention the thing that you just mentioned is correct. One of the hugest challenges is the containment. Because
100%, yeah.
antimatter, when it comes in contact with matter, is a problem.
Right. So if you were unable to contain your trip to Alpha Centauri for even a millionth of a second, that would not be good. It reminds me of the Star Trek where Scotty's saying, Captain, the antimatter pods are losing containment, gonna blow, and that's exactly what happened. So the short answer is yes, antimatter, as in principle, could make and use as a source of energy, but there are probably far less expensive sources of energy. It depends on what you need to do. The Voyager probes are still chugging along with plutonium now. They're running out of energy at this point. We could, presumably do a somewhat better job if we needed to. So I like the idea of antimatter, but the reality is the danger, not the obvious danger of weapons, but the danger of if you
My
wanted to be a
conscience is
ship
already.
run by antimatter, if it ever got loose, well, you would never know it. That would be that.
The reason I find this kind of inspiring is antimatter is in the space of physics that has a lot of mysteries. There's a lot of exploration to be done. And so this kind of connection to energy means that if we have a bunch of breakthroughs on the antimatter side, that might lead to a better propulsion system, better energy generation systems. In principle, there's some combination of engineering here, but there's some combination of understanding the fundamental physics.
We know how to do this. We know you take energy, you make antimatter. You have to contain it, you have to store it, you have to do all the hard things. But I would be shocked if there was some new addition to the theory that made antimatter production easier.
Interesting. So we know how to produce antimatter with accelerators. You're saying there's not breakthroughs of physics that could lead to different mechanisms for the generation of antimatter.
You have to concentrate energy. That's it. If there's another way to concentrate energy, that would work too.
And that's all about concentrated energy for the accelerator.
And remember, we're talking concentrating it into volumes the size of a proton. If you concentrate it to the size of your thumb, well then, it's really the density that matters, the local density. And so when you smash two protons together, all of that's occurring in a tiny, tiny volume. So it's the local density of energy that matters. If you had a lot of energy in a thimble or something, it's probably not dense enough. It really has to be in close proximity for that to happen. And then when it does, it's okay. So if there's another way, we know how to do it to make that density thing with accelerators. If someone has a bright idea on how to make highly dense energy, then yeah, making antimatter is a piece of cake. But that's the crux, concentrated energy.
Yeah, and how to do so in a cost-efficient manner, not trillions of dollars.
Well, yeah.
So one of the big mysteries with antimatter is the bigger why. Where is the antimatter that should kind of be there if the whole idea is that time to generate matter, you generate the same amount of antimatter, and yet when we look out into the observable universe, it seems like there's not antimatter for the most part there. So what do we understand about this mystery? What are the possible explanations as to why?
So there's this thing called baryogenesis, and as you say, so reiterating a little bit what you just said, These are both Einstein things. Einstein says that when you take energy, you make matter and antimatter in equal quantities, and Einstein says after the Big Bang there was a lot of energy in the universe which should have made matter and antimatter. We only see matter. Where did the antimatter go? And the answer is we don't know. However, there are some ideas, and there's a lot of thinking on it. And in fact, for me, is doing an experiment right now with neutrinos, trying to better understand what it was that made the matter and antimatter not be the same. Now, we do have a measurement of how much different it should be, and it's kind of neat. We can do this by counting the number of protons in the universe, just looking at galaxies and so forth. And then we can look at the cosmic microwave background, which is sort of the aftermath of the Big Bang, and we can count the number of photons from the cosmic microwave background. And with a little bit of math, what we can do is we can then say that somehow in the early universe, something made a very, very tiny asymmetry, so that for every billion with a B, antimatter particles that existed in the universe, there were 1,000,000,001 matter particles. The billions canceled, annihilated, destroyed each other, and that extra one that's left over is us. And so, what physics mechanism made that ever so slight asymmetry is not understood. There are some thoughts. One thought is that, well, that's just how it was. When the universe was formed, there was an asymmetry. It was not made by matter and antimatter. Another possibility is there are various numbers of theories, all under the word baryogenesis. Baryo coming from the word baryon, which basically means protons, and genesis meaning the creation of, and we say that simply because the protons are the heaviest particles, and so baryogenesis is just the creation of matter. And there are just a number of theories in quantum mechanics that say that matter and antimatter can oscillate back and forth into one another, and there is a slight asymmetry in how that happens. And we know that this is true to a degree. We've measured it in the 1960s with a different form of matter. I mean, not protons, but a type of ephemeral matter that only exists in particle accelerators. And so we know that there is a slight difference between matter and antimatter, but it's not enough. It doesn't explain that. We're not sure. So at Fermilab, we have this idea which kind of turns things on its head, and it's not baryogenesis, it's leptogenesis. So leptons are the electrons. And because Fermilab is currently the world's most powerful neutrino accelerator, and neutrinos are leptons, there is this idea. Now, leptogenesis is incredibly complicated, but the idea is that it is possible. We know that neutrinos actually change their identity. There are 3 different types of neutrinos, like, cats and jaguars and tigers. And if you have a beam of just cats, if you go along a little while, you find there's cats and jaguars and then tigers, and then they'll be back to all cats again. And so this oscillation thing is called neutrino oscillation. We've known it's been true since 1998. And what we are studying is we're going to make a beam of neutrinos and another beam of antimatter neutrinos, and we're going to study the oscillation behavior of the 2 of them. And it is possible, it is unlikely, but it is possible that the 2 of them will oscillate at slightly different rates. And if the neutrinos oscillate at slightly different rates, then that, along with several other highly improbable things, can tie together and might explain why there is more matter in the universe. So if I was going to bet the farm, I'll bet that they oscillate at the same rate, but I don't know, and you don't know until you do the measurements, so that's what we're doing. There are some other experiments trying to measure it right now, so there's a big race between the Fermilab group and another group in Japan to see who gets there first and make this measurement, and we will find out. If it turns out, though, that there is a difference in this oscillation rate between matter and antimatter, it will be a huge clue in this very, very difficult puzzle. I wish I could tell you I knew what the answer is, but literally nobody knows. I mean, and that's the thing of being a research scientist like me, is if you're not confused, you're not doing your job.
So there's this desperate, or not desperate, exciting search for this tiny asymmetry.
Yes.
It's so crazy to think that everything we see around us is a result of this tiny asymmetry, that there was this gigantic annihilation of matter and antimatter in the
Yes.
early universe. And this is just some little accident.
Yeah, that's
It's
crazy.
a happy accident.
That is just, I mean, it's totally crazy.
This is one of the areas of physics where there's a lot of mystery.
Mm-hmm.
This is Pocket. I never go anywhere without it. At the tap of a button,
Okay, so can we pull at that thread a little further? Let's talk about our intuition of what is dark energy as it connects to empty space and everything we've been talking about. What's the cleanest definition of dark energy?
So dark energy is either energy of space or energy in space. The most common statement is the energy of space. And it is essentially a repulsive form of gravity. And we believe this is real, and the reason we believe this is real is from observation. This is one of those things where we talked about a while ago, where I said that, you can think about things, this theoretical stuff, and try to come up with a measurement, or you can make measurements and see where they disagree with predictions and lead that in a direction. So back in the late 1990s, some astronomers were looking at the expansion rate of the universe. So the Big Bang occurred, the universe is expanding, the universe is full of matter, matter attracts, so the gravity due to the matter of the universe should slow the expansion of the universe. And the only question was, how much? There were three possibilities. The possibilities were there was so much gravitational force that the expansion of the universe would slow, stop, and be pulled back together in a big crunch. Number two was that the universe would continue expanding, slowing down, but never really stopping. And then the third possibility was the exact critical case, where expansion would slow forever and approach zero only at infinity, never quite stopping or reversing. So those were the possibilities, door number 1, 2, or 3. So they did the measurement, and what did they find? It was door number 4. The universe was not only expanding, but the expansion was speeding up. And the only way that could happen, given that gravity slows it down, is there was a repulsive force. And the name we give to that repulsive force is dark energy. This is something that Einstein postulated early on in his development of general relativity, but then because at the time he knew that his theory predicted that the universe would collapse, but he believed the universe was eternal and unchanging, and so he needed something to counterbalance that collapse, and so he invented dark energy. He didn't call it that, called it the cosmological constant. But then a few years later, Edwin Hubble discovered that the universe was indeed expanding, and so since the universe was no longer static, Einstein said, no need for cosmological constant, took it back out. Thought it was a dumb idea that he put it in and was embarrassed. However, in 1998, it became clear that his original idea that there should be some sort of repulsive form of gravity was real, and it's put back in the theory. And so that's what it is. We are pretty confident at this point that the expansion of the universe is speeding up, and the thing driving it is dark energy. Now, what is dark energy? I don't know. As I said, the most common thought is that it is the energy of space itself, but it is at least conceivable that there is a field in space where space exists, and that field is pushing space apart. That's another conceivability that I'm not sure that we have the instrumentation to distinguish, but that's not what normally people think. People think it is literally a property of space.
But there is what you call the worst prediction in physics, which is
that's another one.
a nice little insight about the complicated nature of dark energy. So the observations, as he describes, say that empty space has a tiny energy density that accelerates expansion of the universe. But quantum field theory's prediction for what vacuum energy should be, coupled with gravity, is much larger. So this is what makes for the quote, video on this worst prediction in physics. Can you explain this crisis?
Well, there's a measurement, and you can measure how fast the universe is expanding, and from that you get a measurement of dark energy. However, if you then say, well, suppose the dark energy is due to fields in space. So that's quantum field theory. Hey, I know a lot about quantum field theory. And so we can take the quantum field theory and we can calculate what the density of energy is due to quantum field theory. And basically what you do is you take within a volume all of the wavelengths, the longer wavelengths, the shorter wavelengths, the shorter and shorter, and you can add them all up. And each wavelength adds a certain amount of energy. And if you add that all up, then you get a number. And that number is the rather embarrassing 10 to the 120 power times, that's a 1 with 120 zeros after it, bigger than the measurement of dark energy.
Yeah.
So you go, yuck, that is not fun at all. And that is because the equation comes to the highest energy or the smallest wavelength particle that you can imagine to the fourth power. So anything to the fourth power is a big deal. So that's where you get that awful number. Now, if it turns out that there is some new physics that's just about at the energy scale we can measure using our biggest particle accelerators, remember I told you that that was a factor. The maximum energy scale, Planck scale, is 10 to the 15 times bigger than what we can measure now. So let's say that we don't have to calculate up to the Planck scale because something happens, something changes at the energy that we know right now. Well, then that means we don't have to integrate to Planck scale, we integrate to 10 to the 15th less than the Planck scale, and this thing is to the fourth power, so 10 to the 15th to the fourth power is 60. So now, even if we say, Don, he's brilliant, he's going to find something at the LHC tomorrow, it's going to solve all this problem. Now we've solved it, it's much better. It's only different by 10 to the 60 power, which is still pretty bleeding big. So the short answer is there is very clearly something going on, something wrong, very badly wrong in the quantum field theory. We have to have, maybe there's another field that balances out the energy, that cancels it down. And even that, that's not so outrageous. You could imagine that there's another, like we have matter and antimatter, they balance pretty well. Okay, maybe there's something going on, you could cancel that out, that'd be perfect. Canceling something to zero is easy, because, plus 1 and minus 1, 0, plus 2, minus 2, 0. But we still have dark energy. Dark energy is a little bit. So if it cancels, it doesn't cancel exactly because it left over that little bit of dark energy. So that is its own curiosity. Perfect cancellation, pretty easy. Theorists do that, 8 times before breakfast. Imperfect cancellation, much harder.
Just to elaborate a little bit, what do you think solving, in quotes, solving dark energy would look like?
Well, what you would do is you would hypothesize that there existed some other field that had the reverse effect of existing quantum fields,
But not to zero.
So, but if you had it to go to zero, sure, maybe there's a field that exists at really high energies that we haven't seen yet. I don't know, but it cancels things out and we're cool.
How do we then demonstrate the existence of that field?
Well, that would depend on the prediction.
How do you even come up with a new field?
Like all theorists do. Well, let's add something to my equation and see what happens. I mean, and that's okay. I mean, I'm being glib about that, but that is precisely what you do. You say, what change? We have this thing that works quite beautifully, except it fails here. What is the addition that we need to make that changes very little in the realm that we measured, and yet fixes this hard thing? And So you literally just go, da da da, okay, what do I need? Plus 6 or something. And as long as it makes no changes where it would hurt our measurements and fixes the big thing, then that is at least a candidate theory. Now, that doesn't mean it's right, but it at least gives you an understanding of what the right answer should look like. And so that's the first step, is what should the real answer look like, or what is a possible real answer. And then once you kind of know that, then other people can look and say, well, let me think about a theory that kind of has the required properties to do what we need it to do. So it's a multi-step process, but the first step is, how do we tame this problem without coming up with really terrible predictions that we've already ruled out? And so that's what you do. And you know, that is literally a sensible, viable, theoretical thing, you know, because you have to explore cool ideas.
I mean, one of the reasons dark energy is super interesting is it kind of gives us a mechanism by which we can talk about the deep future of the universe. It's making, we have observations about the expansion of the universe, but it's also giving us the mechanism of that, right? So we
Sure.
can talk about any weirdness, any good model we have that captures some of the weirdness of dark energy might give us insights about how this thing ends, how the universe,
Sure.
about the deep future of the universe, right?
Absolutely. As it stands right now, if dark energy is real, and who knows, you know, if it's real exactly as we've measured it, then as the universe gets bigger and bigger, dark energy becomes a bigger and bigger component of the energy balance of the universe, and it takes over and it drives the continued accelerated expansion of the universe. And if dark energy gets lower, you know, for some reason that we don't understand, maybe it changes over time, gets smaller. That could change things. If it gets bigger, it could change things.
That is one of the big open questions, whether it's constant over time or not.
Right. And there has been a recent measurement that suggests that dark energy is getting smaller. However, that is a new measurement, not confirmed, blah, 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 blah. Nobody should believe it. But it's a hint that maybe it's changing, which is kind of cool in itself, because the current bias until recently is that dark energy is constant. Now, I want to be super careful because it's misleading. People say dark energy is constant. Dark energy is a density. Now, think about that. You have a certain density, let's start with that. Then the universe expands. So energy is volume times density. If the universe gets bigger and the density is constant, that means dark energy is increasing. It's not just increasing as a fraction and overwhelming ordinary matter, but ordinary matter, as the universe expands, its density decreases because it's constant, and the volume gets bigger, the density drops. Dark energy, until recently, is thought to be constant density.
So that's what's implied when you say constant density, which means it's actually increasing because space is increasing. The size of space is increasing.
And so that's a weirdness. And that then ties into the nature of space. Why does that tie into the nature of space? Well, because if dark energy is a field in space, if you increase the volume, you would think the energy density would drop. But if space is increasing and space is quantized, and I don't know if it is, then maybe what's happening is space isn't stretching, but like little space particles are appearing as the space, you know, there's like bubbles of space appearing, and each bubble contains a certain amount of dark energy. And so therefore that would give you a sense that dark energy is a property of space rather than a field in space. But that's all very hand-wavy, guessworky stuff.
So if you had bet all your money, is dark energy like a real physical, what does that even mean, a thing that exists, versus is this just a renaming of the cosmological constant?
Unfortunately, I think it's both. I mean, well, I mean, it is. It's describing a reality, but it's also maybe telling us something about space.
Literally a property of space.
Yeah, I mean, that's kind of what it looks like. Given that it seems to be constant density that seems to me, now this is not something anybody should believe, please, nobody believe this, but it seems to me that this is leaning towards the idea that A, it's a property of space, B, space is quantized, C, as space is expanding, little quantum of space are appearing, and D, each one of those quanta has a certain amount of energy associated with it, and that would kind of explain the constant density. Now, please, that's not, nobody accepts that. This is just nonsense.
But a lot of the stuff that you just said is probably experimentally testably, probably constructive. The bubbles of
Finding out the bubbles of space, but those quanta conceivably are Planck-sized bubbles.
yeah, the quanta.
Well, they'd be quantum of space. I mean, the idea is, you look at a sand dune and it looks smooth and continuous, but you can see individual grains of sand, right? And so what this is saying is as this dune expands, new grains of sand are appearing, and each one of them is a quantum of space.
So what kind of experiments can we do in the coming decades or centuries to understand dark energy better?
I mean, people have been talking about quantum entanglement of gravity. In standard quantum mechanics, a particle can be in two places at the same time. All right? So now you have two particles. So this particle can be in two places at the same time. This particle be two places at the same time. If you put them near one another, well, if they're close to each other, there's a certain gravitational force. If they're far apart, there's certain. And if one is close and one is far, you have another one. You can calculate the effects of gravity having to do with quantum entangled particles being in two places. And people are talking about doing this and trying to see if in doing such a measurement they might be able to definitively determine whether gravity is a quantum phenomenon or a continuous phenomenon. And that is potentially a measurement that could be done soon-ish, because the technologies of inherent in all of this recent work on quantum mechanics is allowing people to be able to make instrumentation that might be precise enough to do this measurement. Now, this will not tell us what quantum gravity is. It will not tell us anything, but it will tell us that gravity is quantized. And just knowing that, well, for one thing, it shuts out a whole realm of continuous gravity, and the theoretical community will then turn its attention, forget this stuff, and think over here. Now, that doesn't tell you that space is quantized, but it tells you that gravity is quantized, if it bears out. So, and if gravity is quantized, then people will start thinking more about space being quantized.
I have to ask, because you mentioned dark matter is perhaps even more mysterious than dark energy.
Okay.
Can you build up the intuition why it's more mysterious? What is dark matter?
Oh gosh, what is dark matter? A, I don't know. B, it's terribly fascinating.
Yeah.
All right. So, first thing, and the most important thing, because I'm an experimentalist, by God, the first thing is, why do we believe there's dark matter? And the reason is that astronomical measurements do not agree with predictions by Newtonian or relativity theory. Galaxies spin too fast, clusters of galaxies move too quickly, and the distortion of very distant galaxies due to the gravitational field of near galaxies disagrees with the prediction from what we see from the observed matter.
These are the fitted long sleeves from Hans. These are tight and fitted all around the arms and chest, and loose all through the midsection. It's that perfect amount showing up.
So there are three very distinct reasons why we are predicting that something is wrong in our understanding of either the laws of physics or the matter budget of the universe. The easiest one to talk about is the spinning galaxies. Now, this is what I'm saying is not unique to spinning galaxies, just easiest to talk about. So, galaxies are observed to spin more quickly than they should if we add up the gravity we see. By all rights, galaxies spinning that fast should blow themselves apart, and they don't. So, what can be the answer? Well, you have the force required for a star to orbit, to move in a circle, you have the force due to gravity, and they're connected by an equal sign. Then the prediction is wrong. So either the force due to gravity is wrong, the force needed to move in a circle is wrong, or the equal sign is wrong. I mean, this is really simple. One of those things is wrong. So, one possibility is simply that Newton's law of gravity, mass times the mass over r squared times a constant, that's just wrong. Another possibility is Newton's F equals ma that we are taught in introductory physics is wrong. Both of those are eminently possible. Over here, maybe we don't understand gravity, or maybe there's more mass than we can see. So these, I mean, it's nice that you can look at this really simply and come up with a list, cookbook with things we can test. And so we've done that. We've gone and said, what are the possibilities? Well, the most obvious possibility is that there is more mass than we can see. There's black holes, there's hydrogen gas that we can't see, whatever. There's something out there. So that was the first thing. So you go and you look, and there's no hydrogen gas because we can see that with radio waves. That's not it. In the 90s, we went looking for black holes, rogue planets, things like that. Those exist, but not enough of them. That's not it. And so now we're left with, there's some sort of matter that we can't see, or we don't understand gravity, or we don't understand inertia. Now, I personally, if you asked me this, 25 years ago, I would have said the most likely answer is that we don't understand inertia or gravity. 20 years ago, 25 years ago, that's what I would have said. No problem. However, there have been a couple of observations that have caused me to change my thinking, and I think that dark matter is more likely. One of them is called the bullet cluster. So the bullet cluster, there are two large clusters of galaxies. In these large clusters of galaxies, well, any galaxy consists of a couple of components. There are the galaxies themselves, there's the hydrogen gas that surrounds the galaxies, and maybe there is dark matter. And if dark matter is real, or dark matter is not real, you will get different answers if those two galaxies pass through one another. The galaxies themselves should pass through one another, basically not interacting, but the big thing is the gas clouds. So if there's big clouds of gas, as the galaxies pass through one another, the clouds should interact, and the gas cloud should stop in the middle and be really, really hot. So then you would see, if there were no dark matter, you would see the cluster of galaxies. Cluster of galaxies is a big gas cloud in the middle, and because the big gas cloud in the middle is much more massive than the galaxies themselves, you would expect to see distortions that we call dark matter distortions in the middle. If, however, dark matter is real, the galaxies pass through one another, the cloud stops. Dark matter doesn't interact with the cloud, so it passes through. In that case, you would expect to see the distortions where the galaxies are. And that's what we see. So that is a strong evidence, in my mind. The bullet cluster is strong evidence that dark matter is a real thing. And there is another example, which is much more recent. Dark bullet cluster was a while ago, called the Dragonfly galaxies. There's Dragonfly 2 and Dragonfly 4. These are galaxies that rotate exactly according to Newton's laws. And so the fact that they rotate exactly according to Newton's laws says that whatever's causing galaxies to rotate too fast is not a property of matter. But if you had a galaxy where there was no dark matter, for whatever reason it got stripped off or something, this is one of those lovely ironies that the existence of a galaxy with no dark matter is very strong evidence that dark matter is real, because you can take the dark matter out. So the DF2 and DF4 also suggest to me that dark matter is real. So now, while it remains possible that we need to modify the laws of inertia, or we need to modify the laws of gravity, those are possible still. In my opinion, and that was Dawn's opinion, but probably most of the scientific community, dark matter is likely a real thing. Now, that's great. I've taken you all the way to dark matter. So now you're going to ask me, you're going to say, Don, what is dark matter? I'm going to but I know what it isn't. Okay? I know that it is not black holes. I know that it is it's not rogue planets. I know that we've done the measurements. We've looked across nearly every mass range for compact objects and ruled them out. So if dark matter is real, it can't be made of those. So then you're left with the idea that dark matter is a particle. And that's what we've thought about. The name for the dark matter particle that we've called for a long time is a WIMP, for a weakly interacting massive particle. And we have spent the last, 30 years looking for them in various ways. There are 3 ways that we might see dark matter. The direct way, which says that dark matter exists literally everywhere in this room, in our laboratory, and the dark matter is passing through the Earth like a wind, and we put up detectors trying to see those. We have done that, and we've seen nothing.
So we should say we've done that for neutrinos.
We've done that for many different types of dark matter. We just simply put detectors in labs deep underground, and we can see neutrinos in them, it's true, but dark matter would have, especially heavy dark matter, what these WIMPs, they have a different signature, and we've seen no evidence of dark matter interaction in these detectors.
If you didn't go to the ER after a car accident, you could still be owed a huge check. No, seriously, I didn't go to the ER and still got paid $82,000.
So neutrinos are also weakly interacting and also have mass.
They are.
But not enough mass. So WIMPs are
Right.
heavy on the
Right. Neutrinos are indeed WIMPs of a sort. Now, we have to be careful what we mean by WIMPs. They are weakly interacting massive particles. But we can calculate, and there's just not enough mass in them. Not it.
Got it.
So we need another form. And we have seen 0 evidence of this wind of dark matter through the Earth. Another possibility is you look where you think dark matter might be concentrated at the center of galaxies. And if dark matter exists and there's antimatter dark matter, maybe they annihilate and make photons. And so we look for gamma rays and various other signatures of annihilating dark matter. And there are always constantly announcements of, oh, we saw it, oh, we didn't. Oh, the problem is that way of looking for dark matter is hard because there are other ways of making, for instance, gamma rays like neutron stars and stuff, and you really need to understand the details of galaxies really, really well to believe that. And then the final option is what I do, where we smash particles together at high mass or high energy. We try to make dark matter particles. If you make dark matter particles, because they don't interact except via gravity, they escape with your detector. So what you're seeing, what you hope to see, is an event where you collide particles, a dark matter particle escapes and you don't see it, but the recoil you see on the other side because momentum is conserved. So you see a blob of energy on this side, nothing on the other side. Maybe that's dark matter. And that also happens with neutrinos. So you need to understand everything about neutrinos and calculate how many of those you see, and then hope you see more. And then that might be dark matter. Again, that hasn't worked. So we've ruled out some dark matter particles, but the problem is the range of space of possible mass, if dark matter is of a particulate form, the range of viable dark matter ranges from something like the mass of an asteroid to far lighter than an electron and everywhere in between. And we have looked, we've ruled out some little spots in that phase space, but that's a big range.
Is it really possible to miss a particle the size of an asteroid?
The astronomical searches were not sensitive to that level of dark matter, but then you would expect that there would be some of those in the solar system, and if they're what we think, like asteroids or something, then we'd heat them up and we'd eventually see them. But if they're really like truly dark matter, doesn't interact with matter, which means they wouldn't absorb energy from the sun, so they'd be really dark. I don't know, maybe they're out there. But the only way we searched for them was a thing called microlensing. So if a massive object, you have a distant star, and a massive object passes between that star and your eye, that star will momentarily brighten. And so you just look for these, what they call microlensing events, and you count them. And you see some, and we did see some, black holes pass in front of stars, and we've seen them, but we just haven't seen enough. And for very low mass particles like asteroids, they just wouldn't make enough brightening effect to see. So there's like a minimum sensitivity of brightening, and that about a third 1/3 the mass of a moon, our moon, is about the sensitivity that we had. So, nobody, I think, really thought that these low mass guys were likely. What they thought was more likely they were just unseen black holes, which I thought, I think is completely reasonable. And then when that got ruled out, I thought, okay, modify gravity or inertia. Well, now the clustering dragonfly seems to rule that out. So I'm stuck in my head with dark matter seems to be real, and we don't know what it is.
And it makes up a giant percentage of matter in the universe.
It is 5 times more prevalent than ordinary matter now.
This is incredible.
It is incredible, and that's why it's cool. So if someone out there is, a young person who wants to get into this, understanding dark matter is a big deal. I mean, it's 5 times more prevalent. The problem is, as I told you, if the mass is ranging from an asteroid to far lighter than an electron, if you get on an experiment that looks at one little range of mass, maybe you weren't the lucky guy that measured the right place, And that's one of the reasons why, as fascinating as I think it is, I'm not doing dark matter experiments because, if you make an experiment that searches one mass range, it'll be blind to another mass range. So what you need is many groups doing all sorts of radically different experiments, exploring all sorts of parameter space.
Why didn't anyone tell me that you can earn an MBA by building a revenue-generating business? So there's this program called One Day, where you're paired one-on-one with an entrepreneur who's already built a multi-million-dollar business in your industry. They build your business idea with you over 18 months, guiding you through every step so you avoid common mistakes. You also work part-time, so you keep your day job until your business generates revenue. And then you graduate with both a revenue-generating business and a fully accredited MBA from one of the top 30 business schools in the world. Tap below to learn more.
Prefer a GLP-1 pill to lose weight?
So, I never intended to be super skinny. I've always been a big guy. But because I noticed how unhealthy I felt when I was bigger, I just wanted to feel healthy. And then my friend told me about weight loss by Hims.
Hims is now offering the Wegovy pill.
An affordable GLP-1 that's FDA approved for weight loss. You can get started for just $39 a month with an active Hims membership. You take an online assessment, then connect with a licensed provider
Who determines if a prescription is right for you. Are you ready to see progress? Take the online consultation to get started.
And with all that said, until you see it, there still is the possibility that maybe we don't understand gravity or inertia right. You can't rule that out.
If there is dark matter out there, you're hoping it's actually somehow detectable.
I mean, I don't know what it is. I think it's cool. It's very, very fascinating. That is one thing I really do hope in my lifetime is understood, because I'd like to know the answer to that.
And that's the thing that you could see a discovery of.
You got to get lucky, though. I mean, you got to look in the right place, whatever it is.
Just imagine.
Or you have to come up with that really cool theoretical idea that everybody's overlooked, which is another possibility. And there are people who are really, really religiously hating dark matter, largely because we've looked so hard for so many years, and the experiments in today's world are a million times more sensitive than when I was a starting student, and they still haven't seen anything. And that's why people really hate dark matter. I mean, some of them, because they think we should have seen it by now, but, I don't know.
I mean, I'm a sucker for direct observation. Indirect is obviously also really great, but direct, just imagine pointing your telescope in a certain direction, and because of some artifact of cosmology, being able to directly detect a giant amount of a thing that you could say is dark matter.
You would see it orbit, things orbit it,
Yeah.
or it would eclipse things in front of it, or...
Yeah, like in an obvious way. Because some of the stuff you mentioned with DF2 and DF4, those are like brilliant, indirect deductions that there should be something like dark matter. But some obvious, blocking, occluding, this kind of thing.
We did that in the 90s with experiments called Macho, Ogle, and some others. They looked for a black hole that you just can't see. Black hole you can't see. It's perfect. It's a perfect candidate for dark matter. And And if there's enough of them out there, then remember, there's 5 times the number of stars, which means there's a whole lot of freaking black holes out there. We should have seen them, and we didn't.
Wow, what a grand mystery. We covered so many of them. I could talk to you for 1,000 more hours, Don. Let me, if I can, ask you about a little bit more of a, on the personal side. You have a really inspiring life story. Your folks didn't go to college. Can you just tell me about your childhood and where you found the love for physics and science, and maybe how you found your journey to become a physicist, given the context of where you came from?
Well, I grew up a poor kid in the boondocks. Great parents, but not ones that could guide me terribly academically, but very nurturing. You know, my mom would laugh that she could stop helping me math after like 6th or 7th grade, you know. But they were supportive. And there were a couple of things that, three things I think that folded into it. One is I was a voracious reader as a kid. I loved science fiction. I would read a book a day. It drove my mother nuts because she would try to be nice. She'd buy me a book, and I'd say thank you, and the next day it'd be done. You know, it just drove her completely nuts. But anyways, but science fiction is good for fostering imagination, and so that's precisely what it did. In addition, and this is where the more serious science came along, there were lovely science communicators that were popular in the 1970s. Isaac Asimov, Carl Sagan, a guy by the name of George Gamow. They wrote books about science aimed at a layperson. You know, as a kid, I surely couldn't read a textbook and understand it, but I could read and you know, get a hint of what science was. And on top of that, you know, I was, as most people who became scientists, irrepressibly curious about everything. And I had sort of a quasi-philosophical mind. I mean, I was interested in questions that have in the past been theological and then philosophical and now are more scientific. Questions about how did the universe come into existence? Why is the universe the way it is? Why are the laws of the universe what we see them to be? How will the universe, was it created? How will it be destroyed? These are, you know, big questions that have bothered humanity for, well, thousands of years. And so, you know, I did. You said I had, you know, philosophy and religion minors in college, and I did because I was curious about that. I was hoping that learning that history might help me understand these questions. And it was in college where I came to realize the answers that I was searching for were not to be found in those directions, but I still learned about how those questions have been asked in the past. And so I became a scientist, and the only question was I going to be a cosmologist / astrophysicist or a particle physicist? And when I had to make that decision, it was the mid-'80s, and at the time, there were a lot fewer cosmology measurements. There was an awful lot of thinking about the universe and not enough measuring, whereas with particle physics, by God, you could do experiments. And so what attracted me was the ability to actually get an answer and not just mull over what an answer might be. And so I became a particle physicist. It was difficult without having, you know, family mentors or anything like that, but you know, I managed. And that actually is why, well, I'm here and why I've spent a fair bit of my time writing books and so forth, because I figure that there has to be some other kid out there in Iowa or Kansas, Montana, or somewhere out in some little town without a lot of access to the kinds of thing that people, you know, who have highly educated parents do. And I'm hoping that, you know, some of them will have read some of the things I've written and will find their own path forward, because I found it very rewarding over the years. And, you know, I've been doing this long enough that I'm sure this is true. I've had kids come up to me at the lab and say, hey, I'm a summer intern because I saw your video or read your book or, you know, whatever. So I know that at least I've made a small impact. I mean, I always would like to do more, and I appreciate the opportunity that your audience affords me, because I think it's important to talk about these things. These are really cool, fascinating questions. They are unanswered, and they are just waiting for youngsters to come and spend some time thinking about them, because one of your viewers might be one of the people who answer these questions that have stymied very smart people for decades.
My best kept secret for starting a business is LegalZoom. When I was ready to launch my consulting practice, I didn't know where to start. A friend told me about LegalZoom and how they've helped millions of business owners form their LLCs, file all the necessary paperwork, making things actually official, and keeping them compliant after lunch. Sure enough, I headed over to LegalZoom, answered a few easy questions, and in barely any time, my LLC became official. It was easier and faster than I thought. I'm trying to run my business, not learn the ins and outs of the law. I'm grateful I found LegalZoom to help with the legal side of starting and running my business, all for a price that's well within my budget. When you need a legal hand, turn to LegalZoom. Start your LLC today. LegalZoom.
See what happens next on TikTok. Download now.
And we should also say that you're a legit scientist. So we'll mention Sean Carroll, who's a legit scientist, legit physicist, but is also a good science communicator. Anyway, I did want to mention, I don't know if this is true, but I kind of heard you talk about this, that when you first showed up to Fermilab, you were like working crazy hours, working extremely hard, 8 a.m. to midnight. First of all, I love that. Can you speak to what drove you, and maybe the value of hard work in those contexts, in the early career, when you discover a thing you're passionate about?
Well, yeah, I mean, obviously being smart, if you're Einstein, then maybe you can slack, I guess, although even he didn't do that, but I'm not Einstein. But the fact is, when I was young, and I was unencumbered, no family, no kids or something, I couldn't imagine anything I wanted to do more. I mean, some people, they want to go out to the club, they want to, I don't know, play soccer or something, but I wanted to make measurements, and I wanted to understand and learn, and that was fantastic. And so as a graduate student, and this isn't for everybody, but I worked outrageously. I would, from Monday through Saturday, I would be at the lab voluntarily, because I wanted to be, from 8 a.m. to midnight. And on Sunday, I would work from 8 until about 5, and that's because from 5 to midnight, I had to wash clothes and buy groceries and things like that. And I loved it, and I still love it. I can't do that anymore, but that's simply because I have other obligations. But had I been rich, I would have done the same thing. It's something I truly, truly loved. And there is absolutely nothing more fascinating to me than having a hard problem and figuring it out. And that work ethic, well, there's a couple of things that separate smart people from, no kidding, scientists, because all scientists are smart, but the thing that separates, that many scientists have, is a drive and a real grit. For me and for so many scientists that I know, trying to measure something and having it not work just kind of ticks me off, and I am not going to let the universe in my lab or whatever beat me. And some people, if the thing breaks, it's like, oh man, that didn't work. And a lot of people, well, I'm gonna go home, I'm fed up. Nah, it would just kind of make me mad, and I'd put more effort into it. And not okay, I was crazy, I worked long hours, but I think the people who are really good at this will do maybe not that much. Some people have to have a better life than that, but a lot, because it's just, you can't imagine not knowing the answer. And that, when you see that as an older guy, don't maybe not to that degree, but when you see that kind of drive, that intensity of trying to get the answers, you know that person's a winner. And so if some student out there, if it doesn't bring you joy, as what's her name, the Japanese gal says, if it doesn't bring you joy, then it might not be for you. And then you could be a person who reads about it, is involved. But if you want to be a real scientist, it has to be just part of what you are here.
And by the way, it is a hard life, but it is also a very fulfilling one. So working hard towards the thing you love is a really fulfilling way to be.
I think that's true for an artist or something. Anybody, a musician. Musician, they just keep practicing because it is who they are.
Well, I'm glad there's people like you at a place I admire, like Fermilab, one of the many places in the United States and the world that is carrying the beacon of great science and great engineering forward. Don, thank you so much for everything you do, for all the teaching you do online, for all the incredible physics work that you do at Fermilab, and thank you so much for talking today.
Thank you for having me.
Thanks for listening to this conversation with Don Lincoln. To support this podcast, please check out our sponsors in the description, where you can also find links to contact me, ask questions, give feedback, and so on. And now let me leave you with some words from Marie Curie, a 2-time Nobel Prize winner, first in physics, second in chemistry. Nothing in life is to be feared. It is only to be understood. Thank you for listening, and I hope to see you next time.
Frontier's 100% fiber internet, powered by the speed of light, made for doing. And now get this amazing deal before it's gone. Switch to ultra-fast, reliable, 100% fiber internet. Frontier Fiber, good to go.
Why did you put this pillow on it? So you can sit? I might have that white mess on my cord.
With Nanit, new parents build confidence from night one. Go from seeing them sometime.
First, what we see them to be, how the universe was created, how it will be destroyed.
Yeah.
These are, big questions that have bothered humanity for, thousands of years.
Huh?
And so, I did. I said I had,
The C version?
Yeah.
philosophy and religion minors in college, and I did because I was curious about that. I was hoping that
Is that charging?
that history might help me understand these questions. And it was in college where I came to realize the answers that I was searching for were not to be found in those directions, but I still learned about.
Do you need a mouse or do you want to use the trackpad?
Have been asked in the past.
This.
And so I became a scientist, and the only question
I'll use the mouse and you can use the trackpad.
A cosmologist / astrophysicist or an article physicist, and when I had to make that decision, it was the 80s, and at the time